Traditional broadcast consoles hardwire the physical faders directly to the digital signal processing core. This rigid architecture means scaling a studio facility requires ripping out hardware, running new copper, and deploying entirely new mixing desks. The dMix architecture separates the audio processing from the control surface. The heavy mathematical lifting stays centralized in the rack, while the operator interface becomes completely virtual. This virtual interface isn't a massive software suite. It operates as a single standalone HTML file. There is no middleware. You do not need to provision a local server, configure a backend database, or install any browser plugins to make it run. This is the dMix X12 radio service running natively within a standard Chrome or Edge environment. It provides a complete 12-channel broadcast layout with direct access to mix minus and routing parameters. This diagram illustrates the transport layer. The browser and hardware communicate via a standard WebSocket connection. Upon loading, the client transmits an init command, and the hardware instantly responds with the full system state payload. To maintain constant synchronization, the software runs an automatic ping-pong sequence. It verifies the connection every 4 seconds and initiates an automatic reconnect if the stream is interrupted. All ongoing operator commands rely on highly compressed messages. Fader moves and routing changes are transmitted as stringified JSON objects prefixed with the number 42. Keeping the heavy audio processing locked in the rack while exchanging these lightweight JSON strings over the local network ensures the virtual UI reacts with zero perceptible latency. A single dMix hardware core manages up to 128 available input channels across a facility's network. To organize this raw I/O count, the system categorizes the inputs into logical groups, separating AES digital feeds, networked AOIP sources, and analog microphone or line inputs. In the Sources panel, the operator filters the 128 hardware inputs using group tabs. Once located, these feeds are dynamically assigned to the primary A or secondary B source slots on any virtual channel strip. On the main operating surface, the channel's OLED display inherits the assigned hardware source name, updating in real time alongside the active A and B selector buttons. This dynamic mapping means a system architect can configure a comprehensive 12-channel layout for the main control room and use the exact same HTML file to deploy a minimized 4-channel surface in a secondary podcast booth. By divorcing the physical input from a dedicated hardware fader, one centralized DSP core simultaneously powers multiple right-sized virtual studios. Remote broadcasts and live telephony require complex mix-minus routing, ensuring that outside callers hear the entire program feed without hearing a delayed echo of their own voice. This panel displays the centralized 12x12 routing matrix. Each green cell actively contributes audio to a specific auxiliary bus. To prevent feedback, a diagonal line of red cells acts as a visual exclusion zone, blocking channels from sending audio back into themselves. This visual rule translates directly into machine telemetry. The red cell prompts the browser to transmit a JSON parameter, dropping that specific auxiliary send value to -200 decibels, muting it at the hardware level. During setup or after loading a snapshot, the operator clicks a single Push All Sends button to initialize all 144 routing parameters across the network in one action. Embedding these routing rules into a visual matrix translates auxiliary bus mathematics into direct operator control, eliminating the risk of accidental feedback loops. While a virtual interface provides layout flexibility, fast-paced live broadcasts still rely on the muscle memory and tactile response of physical faders. To bridge this gap, the software utilizes the browser's native Web MIDI API to ingest standard Mackie Control Universal Protocol data. In the MIDI panel, continuous control inputs from external hardware devices are directly mapped to specific virtual channels. Moving a physical fader sends pitch bend data via USB. The browser intercepts that MIDI signal through the API and instantly translates it into a standard WebSocket mix command, updating the hardware level in real time. This compatibility allows facilities to deploy premium MCU-compatible fader surfaces for operators requiring professional physical feedback. The interface also acts as an automation bridge for the physical room, utilizing UDP datagrams to trigger external studio events. Enabling these per-channel switches means that toggling a microphone on generates a targeted UDP payload, automatically triggering an external relay to illuminate a studio tally light. By leveraging standard web APIs, a single HTML file functions as a translation bridge, linking physical MIDI controllers, the central audio DSP, and external studio automation. Because the interface is built entirely with standard HTML and CSS, it removes the rigid visual constraints of a hard-coded application, offering total aesthetic flexibility. Operators can adjust color schemes and station branding on the fly, saving these preferences directly to the browser's local storage for session persistence. For system administrators, the software exposes a live, time-stamped diagnostic log, tracking every incoming telemetry packet and WebSocket connection attempt directly within the browser interface. This architecture defines a clear operational boundary. The system engineer maintains centralized control over the intensive DSP processing in the rack. The operator interacts with a highly responsive, tailored visual surface that focuses entirely on workflow. The dMix X12 radio demonstrates the future of broadcast facility design lies in decoupling the heavy processing core from scalable, serverless, web-native interfaces.